All right, hi everybody. So we're moving into chapter 7, talking about the Central Limit Theorem. So we're going to be starting to look today at some more different types of sampling distributions, particularly when we're talking about a sample mean and a sample proportion. So to start off, just to introduce, of course, the namesake for the chapter, the Central Limit Theorem says the shape of the distribution of the sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the population. So the big key here is the distribution of the sample mean becomes approximately normal. So this is a big one here, approximately normal. So when we say approximately normal, that just means regardless of what shape the population has. As the sample size gets larger and larger and larger, the distribution of that sample mean, so the mean, right, the average value of any of our samples, those values are going to become distributed normally. So that's good for us because we can work with a normal distribution a lot better than any other type. So the sample size n that is required in order to be large enough depends on the original population from which the samples are drawn. So generally, we say 30 is kind of the magic number for a normal distribution. Or if it comes from a distribution that's already normal, then we're fine. But in order for us to have this approximate normality, we need to have a large enough sample size to work with. Otherwise, it could be completely skewed, and we wouldn't know. All right, so the central limit theorem for sample means. So first we're going to start off defining a few terms. So we have the sampling distribution. So the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. So the key here, it is a probability distribution. So we're still looking at a curve, looking at area under that curve, but we're looking at a bunch of values coming from a sample size of n. And the sampling distribution of the sample mean is the probability distribution for all possible values of the random variable computed from the sample size n. So basically, when we're looking at the sampling distribution of the means, the sample means, we're saying I have a bunch of different samples. So I have my whole population, say 1,000 people, and I'm going to get a sample size of 100, and I'm going to find out what the mean is from that sample of 100 people. Well, if I were to grab a different 100 people, my sample mean might be different, right? And if I grabbed even another different group of people, my sample mean, again, would be different. So these sample means are changing. They have some variety within them. We can look at how these sample means are all distributed, how they're spread out over many, many different types of samples. So this is what we're going to be looking at in this section. So for the mean and standard deviation of a sampling distribution, well, the mean, which we call mu sub x, the standard deviation, sigma sub x, those values we compute normally. That's what we know is the mean and the standard deviation. But when we're dealing with the x bar values, okay, when we're dealing with the sample means, so x bar, dealing with sample means, this is the formula that we're using. So in other words, what this is telling us is the mean for the sample mean distribution is just the same as the mean for the regular sampling distribution. And then the standard deviation, all we need to do is divide by the square root of n, where n is the sample size. And that's going to give us the standard deviation that we're looking for. So, and of course we will see plenty of examples with this. So suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. So write the distribution. Okay, so we have x bar is approximately normal with mean being 11.4, standard deviation being, right, the standard deviation of 3.2 divided by square root of n for whatever value n is. We don't know yet. So if the random sample of 35 oil changes is selected, describe the sampling distribution of the sample mean. So this would be x bar approximately normal, 11.4 mean, and then standard deviation of 3.2 over the square root of 35. Okay, and this is, just as I was saying, this is approximately normal. Okay, so we do have somewhat of a bell-shaped curve here. So if a random sample of n equals 35 oil changes is selected, what is the probability the mean oil change time is less than 11 minutes? So the mean, which is right here in the middle, that's 11.4. And so 11, somewhere down here below, I don't know exactly where, we want the probability, or the area under the curve, that is less than 11 minutes. So we're looking for the probability that x bar is less than 11. Now, in order to find this, we're going to be utilizing Desmos, just like we did in the previous sections. So let's go ahead and switch over to Desmos. Okay, so now we need to input the information here for this normal curve. So we'll do normal distribution. You can also just find it in the function list. Need to put in the mean and standard deviation. So the mean is going to be 11.4. Standard deviation, you can try approximating it, but since we have the ability to type it in exactly, let's go ahead and do that. So it's 3.2 over the square root of 35. And that's going to be our normal distribution. So let me go and find the curve. So there's the curve, right, centered right around 11.4. And now we can find the cumulative probability. And we want the probability that the value of x bar, that sample mean, is less than 11. So the maximum value should be 11. And we see right here, we get 0.22979, etc., etc., as this probability. So let's take this number and we'll go ahead and just round to 0.23. So we get 0.23. So in other words, if we get 35 people who had their oil changed at this shop, and we're wondering what is the likelihood, what is the probability that the amount of time it took them to get their oil changed was less than 11 minutes, well, there's about a 23% chance that that was the case. All right. Let's look at another example. So the length of time taken on the SAT for a group of students is normally distributed with a mean of 2.5 hours and a standard deviation of 0.25 hours. A sample size of 60 is drawn randomly from the population. Find the probability that the sample mean is between 2 hours and 3 hours. So here we have, just write this out, so looking that average time is going to be approximately normal with mean 2.5, standard deviation of 0.25 over the square root of 60. Okay, so that's going to give us our mean and standard deviation. Okay, so the mean right here is 2.5. All right. And we are trying to find the probability that the sample mean is between 2 hours and 3 hours. So we're looking for probability that x bar is between 2 and 3. Okay, so that's somewhere between 2 and 3, wherever those values are on this graph. All right, so let's go ahead and plug this into Desmos. So I kind of already have the framework set up here. So let's just hang on to the function and let's just change the values within it. So our mean in this case was 2.5, and our standard deviation was 0.25 over the square root of 60. Okay. So now, of course, right now this says 1. That's because we're going all the way from negative infinity to infinity. So that's encompassing everything. Let me find the curve. Okay, so you can see the curve very steep here. Okay, so if we wanted to adjust the scale, we would need to kind of manually do that. But you can see it's a very steep curve. Let me go down to the base here so we can see a little bit closer what's happening. Notice how far out 2 and 3 are on this graph. So 2 being all the way out here, and 3 being all the way out here. So if we go from 2 to 3, notice what Desmos tells us. Desmos tells us that the area is 1. Now, this normal curve, technically speaking, will not hit the x-axis. So when Desmos tells us the area is 1, it's not exactly 1, but really we're just saying that it's so incredibly close to 1. It's probably 0.9999999, something crazy like that. Really, really close to 1. And so Desmos doesn't recognize the difference. So because we can't realistically say there is 100% certainty that this will occur, because there could always be data points that lie outside of that, but we're going to say that it's approximately 1, because the likelihood of it being outside of that region is very, very small. Okay, so it's almost a certainty that it would be between 2 hours and 3 hours, given this information, right, for this particular sample of students. Okay, so let's take a look at another one. So in a recent study, the mean age of tablet users was found to be 34 years old. Suppose the standard deviation is 15 years. Take a sample size of 100. What are the mean and standard deviation for the sample mean ages of the tablet users? So the mean of the sample mean ages, that's just going to be the same as what the mean was of the data, so that's 34. And the standard deviation for the sample means is going to be 15 divided by the square root of 100. Right, so that's 15 over 10. So that's 1.5. So when we ask what does this distribution look like, well, we have a very sizable sample size here, so that's good. So that tells me that this should be approximately normal. Right, so we get x bar is approximately normal with a mean of 34, standard deviation of 1.5. Find the probability that the sample mean age is more than 30 years. So remember our mean here in the middle, that's 34. Standard deviation is 1.5, so we're going down by 1.5s here. So 30 is going to be way down in here somewhere. Okay, let me draw that a little more cleanly. So it's somewhere down in here is 30. And we want the probability that the sample mean age is more than 30. So more than 30, that's going to be everything up here. So I imagine this number is going to be fairly close to 1, right? So we want the probability that x bar is greater than 30. Okay, so let's take this data into Desmos. Alright, get rid of our old numbers here. So now we have our mean value of 34, our standard deviation value of 1.5, and our curve is going to be centered somewhere around 34. We really don't even need to see the curve to run the calculation, but it can be helpful sometimes to just see what the curve looks like in general. So notice 30 is pretty far out on the left over here. So we want everything from 30 and up. So if you zoom in really close, you can see it does start at 30, right? It does cut it off there. And then it's just going to grow infinitely on beyond that. And we get a value of 0.996 approximately. So the probability that x bar is greater than 30 is approximately 0.996. Alright, so in our sample of size 100, the probability that the mean age in that group is going to be more than 30 years, there's about a 99% chance that the mean age would be higher than 30. Okay. And then the last part here, it says find the 95th percentile for the sample mean age to 1 decimal place. So the 95th percentile, this is whatever data point it is up here, so we'll call it x naught, such that all the area beneath it is 95%. Right, 95th percentile meaning you are higher than 95% of every other value. So we need to find the probability that x bar is less than or equal to x naught. And we know that this is 0.95. And what we need to do is figure out what x naught value gives us 95%. So this is where our inverse function is going to come back into play. So for our normal distribution, we still have normal distribution mean of 34, standard deviation of 1.5. But now, when we're looking for the z-score, if you will, for that x value, instead of just looking for the percentage, we need to do normal distribution, and then a period, and then inverse CDF. Okay, and you can also find that in the function tab. And then type in what percentage you want it to have to the left of your value. And in this case, that's 0.95. And we get the value, 36.467. And it said round to 1 decimal place, so that's going to be 36.5. So we get x naught is 36.5. So the 95th percentile. So the mean age that is above 95% of all other possible sample mean ages is 36.5 years old. Right, so looking at the normal curve and identifying both percentages, probabilities, and then also using those probabilities to identify different x values on the curve. Okay, so next up, we're going to look at something new, something a little different, but still applying the same concept. So we're looking at sample proportions. So suppose that a random sample of size n is obtained from a population in which each individual either does or does not have a certain characteristic. The sample proportion, denoted p hat, is given by this formula here. P hat equals x over n, where x is the number of individuals in the sample with the specified characteristic, and then of course n is the sample size. The sample proportion p hat is a statistic that estimates the population proportion p. So we're looking at what proportion of people in our samples have a certain characteristic. So for example, in a Quinnipiac University poll conducted in May 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. Of those 1,745 registered voters, 349 responded yes. Obtain a point estimate for the proportion of registered voters who approve of the way George W. Bush is handling the economy. So the point estimate would be our p hat value. So p hat equals the number of people who have the characteristic. So in this case, that characteristic, quote unquote, is responding yes. That's the people that we're looking at. So there were 349 people who responded yes out of the 1,745 people in total in the survey. So if we get this as a decimal, it's actually works out pretty nicely. It's 0.2. So p hat is 0.2. So in general, if we wanted to then extrapolate this, if we wanted to, kind of make claims about larger groups based on this sample, we would then say about 20% of registered voters approve of the way that he's handling the economy. Okay, so again, we didn't sample the entire population, but we can have conversations about if our sample size is large enough, if it is done truly randomly or not, to discuss kind of the validity of this proportion of people that we get in the sample. So when we're looking at the sampling distribution of a sample proportion, there are three things that we're looking at. As with any normal curve, we're looking at its shape, its center, and its spread. So the shape, we're talking about the normality, the bell curve shape. So when n gets large enough, so as n increases, the shape of the sampling distribution of the sample proportion becomes approximately normal. So just like the sample mean, which is good, we want it to be as normal as possible. The center talks about the mean. So the mean of the sampling distribution for the sample proportion is the same as the population proportion. That's p. And then the spread, the standard deviation of the sampling distribution, decreases as the sample size increases. So the standard deviation decreases as n increases. Okay, so the more data we get, the less variability, the less variety we have within that distribution. So if we look at this example, according to a Time poll conducted in June 2008, 42% of registered voters believe that same-sex couples should be allowed to marry. Describe the sampling distribution of the sample proportion for the samples of size n equals 10, 50, and 100. Now, with these numbers, we really just want to look at not the numbers themselves necessarily, but more comparatively. As the sample size increases from 10 to 50 to 100 to 1,000, whatever the case may be, what is actually happening here? And the first thing that's happening is the shape of the distribution is getting closer to normal. I would say 10 people is probably too small. 50 is a little bit better, 100 is when you start to get better results, especially because you're trying to get a clear picture of all registered voters. So even any of these sample sizes are fairly small. But the larger the size, the closer to normal we get. The mean is getting closer to 42%. Because again, the mean, we assume the mean value is the same as the population proportion mean. And the standard deviation gets smaller. So we expect the standard deviation to shrink as the sample size gets larger, as we just said. Okay. So the specific formulas here that we're going to work with, so these are kind of our big three. So for a simple random sample of size n with population proportion p, the shape of the sampling distribution of p hat is approximately normal provided np times 1 minus p is greater than or equal to 10. So this is our test to determine if the sampling distribution is approximately normal or not. The mean of the sampling distribution is p, so that works out nicely because we should already know what p is. And the standard deviation of p hat is the square root of p times 1 minus p over n, where n is, again, that sample size. Okay. And then what it talks about down here, so the binomial distribution, it mentions that one as well. But this one, we can look at independence of values. So when sampling from finite populations, this assumption is verified by checking the sample size is no more than 5% of the population size. So if you are getting samples that are too big of a portion of your population, you risk having some form of dependency among these groups, because you might start getting people that are somehow related in some way or have other connections and other relationships outside of just being purely random. So we want to make sure that we maintain this independence here. So if we're sampling the entire country and you want to make sure that if you can't sample the entire country, right, you want to make sure that you don't take too big of a population size sample, because then you can start getting unexpected dependencies in there. So again, referring back to that same poll, we're looking at a simple random sample of 50 voters and determine which voters, believe that same-sex couples should be allowed to marry. So that was the poll. Describe the sampling distribution of the sample proportion for registered voters. So describe the sampling distribution. Okay, well, we know that n is 50. That's our sample size. We know that p, the proportion, is 42%, so that's 0.42. Okay, so let's check normality. So we get n times p times 1 minus p. So that's 50 times 0.42 times 0.58. This is 12.18, which is certainly greater than or equal to 10. So we do have that this data is approximately normal. Okay, our distribution is. So that tells us about the shape. And then the center, if we look at the mean of p hat, then this is just going to be p. So that's 0.42. So that tells us where the center is. And then standard deviation of p hat, that's going to be the square root of 0.42 times 1 minus 0.42 over n, which in this case is 50. And we run that calculation, we get 0.0698. So again, this one tells us shape, center, and spread. So it's approximately normal with a center around 0.42 proportion, and then standard deviation, that spread, being about 0.07. All right. So let's look at a more kind of full-fledged example here. So according to the CDC, 18.8% of school-aged children aged 6 to 11 years were overweight in 2004. In a random sample of 90 school-aged children aged 6 to 11 years, what is the probability that at least 19% are overweight? All right, so we have, first of all, our value for P is 18.8%, right? So P is 0.188. That's 18.8%. And then our mean for P hat is going to be 0.188, right, because that's just P. Our standard deviation for P hat is going to be square root of 0.188 times 1 minus 0.188 all over n, and this is a sample of 90 children, which, if we compute that, this is approximately equal to 0.0412. So, again, we have, here's our mean of 0.188, and we're looking for the probability that at least 19% are overweight. So 19, that's 0.19, that's going to be somewhere up here. So 0.19, and we're looking for that probability, that area above 0.19. So I want the probability that P hat is greater than or equal to 0.19. So let's take this information and run it through Desmos. Okay, so let's get our normal distribution here. Get the mean, we said, was 0.188. Standard deviation was, go ahead and use the exact one, square root 0.188 times 1 minus 0.188 over 90. Find the cumulative distribution there, which is going to be down in here. So here's our curve, right? Our bell-shaped curve, centered around 0.188, and we're looking for probability of it being at least 19%, so at least 0.19. Okay, so there we have our area. Looks like almost half, right? And in fact, if we look at the number there, we get about 0.48. So we get this value is approximately 0.48. So about 48%. So the probability that at least 19% of them are overweight is about 48%. Now, suppose a random sample of 90 school-aged children, aged 6 to 11 years, results in 24 overweight children. What might you conclude? So, you might think we're going to find the probability of exactly 24 being overweight, but that's not exactly how this works. If you remember, the probability of any one specific value is actually 0. It has no area under the curve. So what we're going to do is we're going to look at the probability of at least 24 of them being overweight. So to do that, we need to work with the proportion. So we need to find p hat. So that would be 24 overweight children out of the total 90, which gives us approximately 0.2667, right? It would be 26666 repeating forever, but we'll round it off at some point. So on our curve, so our mean of 0.188, and we're looking for probability of it being greater than 0.2667. Okay, so the probability that p hat is greater than or equal to 0.2667. So let's go ahead and find what that is. So lucky for us, it's the same normal curve. So let's go ahead and just put our new number in here. So 0.2667. So you can see a much smaller portion of the area here. So that's 0.028 approximately. So that's 0.028. So, what does this tell us? Well, this tells us that the probability of at least 24 of the children being overweight is 2.8%. So it is highly unlikely. All right. So generally our threshold for something being unlikely, we typically think of it as 5% is the threshold, so 0.05. But this is certainly, I would certainly classify this as unlikely, right? So the probability of at least 24 of the children being overweight is 2.8%. So very, very unlikely that this event would occur. All right. And then for section 7.3, this is basically just kind of a recap of what we've just talked about. So using the central limit theorem, looking at that normality, right, as the data sets, the samples get larger and larger. So we have the two cases here, the sample means and the sample proportions. Those are the two big ones that we're working with here. So this gives us kind of the procedures, and we're just going to look at some examples here dealing with these different cases. So the city of Raleigh has 9,800 registered voters. There are two candidates for city council in an upcoming election, Brown and Feliz. The day before the election, a telephone poll of 250 randomly selected registered voters was conducted, and 142 said they'd vote for Brown, 90 said they'd vote for Feliz, and 18 were undecided. Give the sample statistic, p hat, for the proportion of voters surveyed who said that they'd vote for Brown. The sample statistic p hat suggests that we might expect how many of the 9,800 registered voters to vote for Brown. So let's find p hat first. So p hat, the sample proportion, is going to be, so 142 said they'd vote for him out of the total 250. So that equals 0.568. So about 57% of the people sampled said that they would vote for Brown. Now, to kind of extrapolate from that data, of our 9,800 registered voters, based on this sample alone, how many would we expect to vote for him? So that would be 9,800 times 0.568, which is 5,566.4 people. Now, obviously, we could round this to the nearest person, right? So, say 5,565, or excuse me, 66 people. You could round up if you want, right, to make it the next whole person. Say 5,567 people. But anyway, we're right in that value. So we can use the proportion to estimate values for larger data sets. And this is oftentimes why we like working with these different statistics. Okay. So the first thing that we want to look at, so we have a couple examples here, but when we're dealing with the sample proportions and the sample means, it's important to be able to recognize the difference when to use one over the other. So let's look at this first example. So in an effort to cut costs and improve profits, any U.S. companies have been turning to outsourcing. I think it should say many. In fact, according to Purchasing Magazine, 54% of companies surveyed outsourced some part of their manufacturing process in the past 2 to 3 years. Suppose Purchasing contacted 555 of these companies. So the first question would be, are we dealing with a mean or a proportion? And the big key kind of giveaway here would be this percentage, right? That is a proportion of the whole. So that's going to be our p-value. P is 0.54 with a sample size of 555. So we're going to be working with the sample proportions here. So let's go ahead and get the mean and standard deviations now for this. So the mean of p hat is going to be the same as p, so that's 0.54. And standard deviation for p hat is going to be square root of 0.54 times 0.46, right? That's 1 minus 0.54 over n, so over 555, which is approximately 0.021. Right, standard deviation getting pretty small because the sample size is getting pretty large. All right, we're dividing by a larger and larger number. So, what is the probability that 338 or more companies outsourced some part of their manufacturing process in the past 2 or 3 years? And we'll round to 2 decimal places, write our answer as a percentage. So, in this case, let's see, we have p hat, our sample proportion, the probability that 338 or more, so 338 out of the 555 that were sampled, that's going to be approximately 0.609, so a little more than 60%. All right, so here's 0.54, and then we're looking at 0.609. Since the standard deviation is so small, 0.609 is going to be somewhere way up here. 0.609. And we're looking at this probability in there. So we want the probability that p hat is greater than or equal to 0.609. Okay, and we can go ahead and put this into Desmos given our mean and standard deviation. Okay, so let's do that right here. So the mean is going to be 0.54. Standard deviation, square root of 0.54 times, oops, so 1 minus 0.54, so that's going to be 0.46 over 555. So notice that curve thinning, right, because the standard deviation is getting a lot smaller as we go. And we're looking for the area under the curve, that probability of it being greater than or equal to 0.609. 0.609. So, right, it kind of got lost there, but way down here, that's our area that we're looking at now. And if you look at the number we got 0.000554. So very, very small number. So we got 0.000554. Now, converting this to a percentage means multiplying it by 100. So we would move the decimal place twice. And then rounding that to 2 decimal places means cutting it off there. So that's going to be 0.06 rounded percent. So that's the percentage, right? So that's 0.06%. Very, very improbable, right? Very, very unlikely that this would happen, right? And if you think about it, if the regular proportion is 54%, right, 0.54, the probability that it's that much higher, 338 times out of 555, is not particularly likely. Okay, so then part B, what is the probability that 285 or more companies outsource some part of their manufacturing process in the past 2 or 3 years? So now in this situation, we're looking at 285. Okay, so we get, again, our p hat value. So that's 285 out of 555, which is approximately 0.5135. So here's our mean value in the middle, 0.54. So 0.5135, somewhere down there. So we're looking for the probability that p hat is greater than or equal to 0.5135. Luckily, our setup is the same here. So all we need to do is change that lower bound. So 0.5135. You can see on the curve where this happens. Okay, so a little bit below the mean value there. And if you look at the numbers, we see we get about 0.8948. So 0.8948. So as a percentage, that would be 89.48%. So the likelihood that 285 or more companies outsourced is very high, almost 90% likelihood that 285 or more outsourced. And then part C, what is the probability that 48% or less of these companies outsourced some part of their manufacturing process in the past 2 or 3 years? So in this case, they pretty much just gave us p hat. So they gave us p hat as 0.48. So the probability of that sample mean, or excuse me, sample proportion being less than 0.48. Okay, so here's again 0.54, 0.48, somewhere down in here. And we find this on Desmos. This time 0.48 is the maximum. Oops. So we get 0.48. And we see a very small number, right? 0.00228. .00228. So as a percentage, we're looking at 0.23%. So again, extremely unlikely that few of the companies would outsource in any of these samples. Okay. And then for this last example here, so engineers must consider the breadths of male heads when designing helmets. The company researchers have determined that the population of potential clientele have head breadths that are normally distributed with a mean of 6.7 inches and a standard deviation of 1.2 inches. So suppose we select random samples of size 41 from the population. What is the probability that the breadths of male heads average more than 7.3 inches? So here we're dealing with sample means. So we need the mean and standard deviation. So the mean is just going to be the same, so it's 6.7. Standard deviation is 1.2 over the square root of n, which is 41, which gives a standard deviation of 0.1874. 0.1874. So our mean value here in the middle, that is 6.7. We're trying to find the probability that sample mean is more than 7.3 inches. So that's going to be somewhere way up here. That's going to be 7.3, and we're looking at that area above it. So in this case, we take the 6.7, the 0.1874, right, or take the exact value. Plug those into Desmos. That'll again give us the probability that we're looking for. So get the normal distribution going with mean of 6.7, standard deviation of 1.2 over the square root of 41. Let's find the cumulative probability being greater than 7.3. And you can see, right, very, very small portion. Let's see where it is on the graph here. Here we go. So you can see here it is way down here. Very tiny portion of this graph. Right? So we're looking at numerically 0.00068. So we have 0.00068. So incredibly small likelihood, right? So less than a tenth of a percentage, right? So 0.07% basically, if we were reading it as a percentage. So very, very unlikely that the average of each sample would be 7.3 inches. In what range would we expect to find the middle 36% of most head breadths? So, in this case, we don't know what the values are that we're looking for. So we know here's the mean in the middle. what we're looking for now, so I know I want this portion of the data, so that's 0.36, the middle 36%. And what we're looking for is the range. So we're looking for what is the lower value, I'm going to call it x1, and what is the upper value, I'm going to call it x2. Now we know the probability that x bar is between x1 and x2 is 36%, right? So 0.36. The question now is, what are x1 and x2? Right, so we need to find x1 and x2. So in order to do this, we're going to use that inverse CDF function on Desmos. But again, that one only gives us the area to the left of it. So we need to kind of work with this kind of carefully here. So if we are looking at x1 first, okay, so we're looking at that value. Well, we know that everything to the left of the mean, that is half of the area under the curve, that's 0.50. That's 50% of all the data lies to the left of the mean. And we know that this piece in here is half of the 36. Half of 36 is 0.18. Which means that what's left, this whole portion over here, which is what we're looking for, that's going to be 0.50 minus 0.18. It's going to be, again, the whole thing minus this smaller portion we don't need, and that's 0.32. So when we're looking for the probability that x bar is less than x1, being 32%, that's going to give us the x1 value. So we have our curve here. We can get rid of the cumulative probability. So put dot inverse CDF. And the probability we said was 0.32. And that gives us a value of about 6.61. So we get 6.61. And x2, we're going to do the same thing. So we know that the green area was 0.32, and the blue area was 0.36, right? So if we're looking for everything less than x2, that's going to be all of this is less than x2. So it's going to be 0.32 plus 0.36, right? So 0.32 plus 0.36. That's going to be 0.68. So, if we run the same calculation, but with 0.68, we get 6.79, right? Rounded to 2 decimal places. So we get 6.79. So, the middle 36% of most male head breadths would be between 6.61 inches and 6.79 inches. Okay. And this is going based on our assumption of a sample size of 41 that we saw in the earlier part as well. And then for part C, very similar. If we were to draw samples of size 57 from this population, in what range would you expect to find the middle 36% of most averages for the breadths of male heads in this sample? So, in this case, since we're saying that n is changing, so n is 57, our mean for x bar is remaining unchanged, right? That's still 6.7, just like before. However, the standard deviation this time will change slightly. So that's going to be, this time, 1.2 over the square root of 57. Okay, instead of earlier, it was over the square root of 41. And then we want the probability of x bar being between x1 and x2. We want that to be the middle 36% of the data, just like before. So we're going to use the same percentages, same probabilities we did last time. The only difference now is that our standard deviation has changed. So it's going to be 1.2 over root 57. So let's go ahead and make that change. So that's going to be 57. So that x1 value, 32% of the data less than it, 6.45. So 6.45. And the x2 value has 68% of the data less than it, 0.695. Oops. So that's 6.95. So this is between 6.45 inches and 6.95 inches. Oops. Okay. Oops. So, oh, sorry about that. I thought those numbers looked a little weird. 3.2. Okay. Sorry about that. So I had it over the square root of 5. It's supposed to be square root of 57. So that left number should be 6.63. Sorry about that. So 6.63. Yeah, that's making a little more sense. And our upper number, so the 0.68, is 6.77. All right. 6.77. Yeah, because as we increase the sample size, we should start to get a better picture, like more closely centered around that middle. So that means our middle 36% would be between